Hello and welcome to this presentation. My name is Henrik Hellström and I'm a PhD student at KTH, the Royal Institute of Technology. The title of the talk is Unbiased Over-the-Air Computation via Retransmissions, and it's based on a work that I've done together with my two supervisors, Professor Victoria Fodor and Professor Carlo Fischione. To begin the talk, I'd like to give a brief one-slide background into over-the-air computation. So over-the-air computation is a wireless communications method that was originally thought of back in 2007, but has gained increased popularity in the past years. In over-the-air computation, we consider that we have some group of devices, each carrying a distinct message X that they wish to communicate over the same wireless channel. All devices reach an access point in a single hop, and the goal of the protocol is to recreate a function of these individual messages at the receiver. Generally, there's quite a broad class of functions that can be recreated, but for the purposes of this work, we're interested in the sum. The working principle here is that each device encodes their message into a waveform, and then all of them transmit simultaneously over the same frequency resources, as to promote interference over the wireless channel. Because of the superposition property of electromagnetic waves, the receiver antenna will therefore only experience a single waveform. And if the modulation and demodulation have been done correctly, this should be a sufficient statistic to estimate our sum. It's worth to note that this stands in contrast to the more traditional orthogonal communications systems we use today, where each device is allocated their own radio resources. And due to this complete sharing of the spectrum, we can get much higher throughputs. In fact, we have approximately k times higher throughput with over-the-air computation than orthogonal communications. In this slide, I've illustrated our complex baseband representation of the system using a block diagram. Once again, we have the messages X that the transmitter wants to send, but each device multiplies it by a pre-transmission scalar B before sending it on the channel. The message is then multiplied by a channel coefficient H and summed up via this superposition principle together with some additive noise. Finally, in the receiver hardware, we apply a post-transmission scalar eta to form the received signal Y. And remember, using this Y, we are interested in estimating the sum of the X's. But here we see that we instead have a weighted sum of X at the receiver. This is because the channel coefficients are heterogeneous, so devices with a worse channel will have a smaller contribution to this sum. To solve this problem, a common method is to use channel inversion. Here you're simply just selecting the pre-transmission scalar such as to perfectly compensate for this weight in front of X. In other words, you get a received sum like this. And note that this would be an unbiased estimate of our desired function because we assume that the noise is additive white Gaussian noise and therefore zero mean. However, in practice, it's unfortunately often impossible to implement this scheme due to transmission power limitations. Note that if any device is in a deep fade, then this channel coefficient in the denominator here would be very small, and as a consequence, we need a very large pre-transmission scalar to compensate for it. And since the transmission power is related to the square of this pre-transmission scalar, we can get very high powers required to do this channel inversion. With this in mind, it's natural to consider a problem formulation that looks something like this. So now we have added a constraint here, where every device must be within some maximum power limitation. Up here you have the mean squared error between our received signal and the desired function, and we're minimizing this over our pre- and post-transmission scalars. This problem has already been solved in the prior literature, and you can see the solution here. And given certain simplifying assumptions, this solution is the globally optimal solution. In other words, if you work with the same system model, you cannot get a lower mean squared error than this. However, this solution still has some weights in front on the xk. So the mean squared error is low, but we still have some bias in our estimator. In fact, if you look at if you do just a simple simulation with this precise scheme, you can see that the squared bias approximately comprises half of the mean squared error. So it is a quite significant amount of bias in over-the-air computation systems. This brings us to the contribution of our work, where we are looking to make an unbiased estimator by leveraging retransmissions over fast-fading channels. So the basic principle here is that if you only get a single sample from your fading distribution, or well, a single sample for each device, it's very statistically unlikely that every single device has a good enough channel to be inverted. And as long as you have some sort of channel that cannot be inverted, you inevitably have some estimation error at the receiver. But if you were to transmit the same message X multiple times in the uplink, then you can sample independent channel coefficients from the wireless channel. And quickly, the probability that all of these devices have at least one good channel, it raises very quickly with the number of retransmissions. So specifically, we're looking to get rid of this bias. And with that in mind, we've made a problem formulation that looks like this. So here we have the same system model as before, but now if you look at the optimization problem, you can see that we take the expectation over the noise within this parenthesis here, thereby forming the squared bias here in the as the optimization function. Another difference from the state of the art is that we now have a matrix of pre-transmission scalars rather than a vector, since we both have a device and a time index for each of our retransmissions. And such a problem formulation as we have here could feasibly be solved using convex optimization methods. However, the resulting solution is a non-causal power control algorithm. What I mean by this is that in order for the devices to implement the power control algorithm that comes out of this optimization problem, they would have to know future channel coefficients that haven't been estimated yet. Such a solution might be interesting as, for instance, a theoretical baseline, but in this work, we're interested in creating something more practical. Therefore, we have considered the problem of finding the optimal B that minimizes this squared bias, given the constraint that you can only use past channel coefficients and the current channel coefficient. In order to find such a solution, we turned our eyes to the computer science literature, specifically to the tools of greedy algorithms, and we were able to prove the following theorem. So given this causality constraint, these powers are the best possible choice that you can make to minimize the squared bias. And as you can see, at time t, we're leveraging old channels, so we need some memory to remember channels from the past, and the current channel, but we don't leverage any channels from the future. Let's take a look at this result a little bit more deeply. First, look at this term here. In this paper, we have chosen to name this term the contribution. So the contribution of device K at time t is given by the following sum. So we see here that the optimal power at time t involves the contribution at time t minus 1. So somehow the device is remembering its contribution from the prior iteration, and it's using that to make its decision about the current iteration. The reason we named this the contribution is because if you look at the received signal, you see that this is exactly the weight we have in front of our message xk in the sum. In other words, if you limit yourself to a maximum of capital T transmissions, then after T transmissions, you want to make sure that all of these contributions equal 1, because then every device has reached a full contribution to the sum at the receiver. And in fact, this power control algorithm here is a greedy algorithm that always tries to maximize this contribution in every single iteration until the contribution reaches 1, illustrated in these two plots here on the right. So in the upper plot here, we're looking at the pre-transmission scalar for one particular device in the network over a span of 10 different time slots. So since it's greedy, it will transmit with the maximum power for as many iterations as required until it is able to reach a contribution of 1. At this iteration, it transmits with exactly enough power to get a unit contribution, and then it stops transmitting completely. And given that all devices are able to reach a unit contribution like this, we have successfully implemented an unbiased estimator. Of course, I should mention here that we're definitely paying a price here. Compared to a single transmission over-the-air computation protocol, we're now consuming multiple times more communication resources, where that factor depends on the number of retransmissions that we're using. We also have some numerical results where we have simulated this protocol that we have designed, and you can see it here. So here in the x-axis, we have the maximum number of transmissions that we allow the system. And for each of these values of t, we have done a large number of simulations and taken the average to form this plot. We have two different systems here. The red lines correspond to a system with a post-transmission scalar of 1/2, and the blue lines correspond to a system with a post-transmission scalar of 2. And as you can see, for both of these systems, the bias is decreasing rapidly as you allow for more retransmissions, and it seems to be approaching 0 for both systems. For the system with a lower post-transmission scalar, you need fewer communication resources to hit the 0 bias, but you have larger variance in your estimator. So there is a trade-off here between the amount of communication resources needed to get an unbiased estimate and the amount of variance that you'll have in your final estimator. We're also interested in looking at the probability of achieving completely unbiased estimation. In this plot here on the right, we now have 3 different systems for 3 different values of this post-transmission scalar. As we see, with a few transmissions, it's basically impossible to get an unbiased estimate. In fact, for this estimation, for this numerical result, we used 100 devices in the network. So with a single transmission, all 100 devices would have to get a sufficiently good channel, which is of course extremely unlikely. However, with a finite number of retransmissions, we can see that we very quickly approach 100% probability of achieving unbiased retransmission. So this shows that this time diversity effect is very effective at achieving our goals here. Finally, you might have noted that we have 2 lines for each system. That is because we also have developed an approximation for this probability in case you wanted to get some analytical results and not just numerical. In the paper, we prove that it's impossible to get an exact closed form expression for this probability, and therefore we instead developed this approximate expression that you see here. And from the numerical results, it's appeared that our approximation is relatively good at matching the true probability of unbiased estimation. So to conclude, we know that over-the-air computation has the potential of providing massive benefits in terms of bandwidth and energy efficiency. In fact, we get a throughput that is approximately k times higher, in other words, proportional to the number of devices in the network. However, state-of-the-art solutions in over-the-air computation have a significant bias in the estimator, and this can be a problem for certain applications. In our work, we have proposed that time diversity could be leveraged if you apply retransmissions through fast-fading channels. And with our scheme, we have been able to achieve drastic reductions in both bias and mean-squared error. Finally, we show that our proposed scheme can probabilistically guarantee unbiased over-the-air computation using a finite number of retransmissions. That's the end of my talk. I hope you found it interesting.